Good afternoon, this is Schweitzer, and we're going to run through a couple of examples here and maybe add in a few little variations of calculations, things that we want to kind of be, if we can handle these and be used to these, then this should be a pretty straightforward section. Remember, these calculations are almost always identical. There's a little bit of theory, and then the calculations are always very the same. This page actually talks a little bit more about the theory. So in this case, who is stronger, HF or NAF? So we're able to draw this equation for both. So we have HF plus, and you should be pause this video. You should try this on your own. H2O yields H3O plus F negative. F negative plus H2O yields HF plus OH negative. So this is a reaction that goes both ways. With that being said, this bottom reaction is actually the backwards arrow here. And therefore, they're battling back and forth against each other. So what determines which side of the tug of war you end up on? More this side, referencing the top equation, more acid, or would it be more base? So in this case, the more we go this way, the more H pluses are formed. The more we end up this way, the more hydroxides we'd form, because the more the F negative would be able to push back. Alright, so the two factors here, one would be the Ka and then the Kb of each of these. And of course, Ka times Kb equals Kw. Alright, so those are the strengths of each of these. And then, of course, we have our concentration of each. And all four factors are something we want to take into account to know where we end up on our pendulum. Are we swinging more one way or more the other way? So let's try a couple examples of these and pause the video and see if you can get it right. The solution contains 0.1 molar HF and 0.1 molar NEF. Now, in this case, my strength-wise, the Ka value is 6.6 e to the negative fourth. Now I can use this method to solve out for this, but the teeter-totter on this thing is 1.0 e to the negative seventh, so I know that this Ka went up and this Kb is down. So in this case, who is stronger? The HF is stronger. Okay. So for this point, let's try a few of these problems. Okay. Both contain 0.1 molar and 0.1 molar, so these are identical. So now it's just down to strength. Are we going to be in a solution? Will be acidic, base neutral, will be acidic. And the reason why is because Ka is larger. That was tipping the tide one way or the other way. So you might be able to see how this kind of works. Solution is 0.1 molar HF and 1 molar NEF. Or we acidic, basic, or neutral. Now again, this guy, the strength, this guy is higher, but the concentration for this guy is higher. So in this case, we might be either, without doing a calculation, we might be either. You know, in this case, again, because we're sort of conflicting, I would say that this thing is likely 10 to the negative fourth. If you solve it out, this would be 10 to the negative, like, I don't know, 10th. So it's considerably weaker. So that being said, I'm going to probably would lean more towards acidic even still. Because of the magnitude of how much bigger the strength is. But that being said, you may not know unless you actually calculate it. Alright, a solution contains 1 molar and 0.1 molar NEF. Okay, now, not only are we stronger, but we have a larger concentration, we are going to be acidic. A solution contains 0 molar HF. Nothing, no HF, and only this. Well, in this case, it doesn't matter we having those. We have a base, and therefore we are basic. 0.1 molar HF, and none of that, so we are going to be acidic. Alright, so good little something to think about. Alright, so we have an example here of a different little version of this. Okay, we have a 0.15 molar Schweitzic acid, ionizes 3.4%. Alright, so what's the pH, and what's the Ka of this acid? Alright, so piggybacking off of some of the stuff we did last chapter, Ka equals, okay, concentration of Sz negative, H3O plus, and then we have concentration of HSZ. Alright, I want to fill this table out to get this guy. Remember, water is a liquid, so it's not included. Alright, so let's try and fill out this ice table. We got 0.15, and this is not playing a role. I got 0 of this and 0 of this, but in this case, 15% actually makes it across. So let's take this out. I should say 3.4%. So 0.15 times, all right, 0.034. 0.034. And that tells us the percentage that flips over at that temperature and that concentration. 0.15 times 0.034, and I got what, 0.0051 equals 0.0051. So that's not so bad. Minus 0.0051. I'm also going to lose that of the water, but it's not changing concentration. Plus 0.0051 plus 0.0051. That puts this guy at 0.15 minus my previous answer is 0.1, not much, 0.1449, 0.0051, 0.0051, and now let's just fill in the table. We got 0.0051. I'm just going to square that thing to the top, and then 0.1449 and equals, okay, 0.0051 times 0.0051 equals, divided by 0.1449 equals, and then I got 1.79 e to the negative fourth. 1.79 e to the negative fourth, and this is my Ka value right here. And then, of course, my pH is just the negative log of this particular guy here, 0.0051. Here we go. Negative log 0.0051, and there we go, 2.29. 2.29, and that's my two things I got there. Who is stronger, Schweitzic acid or the anion, the conjugate? Well, this guy here is 1.79 e to the negative fourth, and our teeter-totter, all right, that means this one's stronger and this one's weaker. If Se is stronger, why is it acidic and it's not stronger? All right. Next one, finally, what does it mean if an acid has a larger Ka value? In this situation, it just means it's stronger. And inherently, it pushes from reactants to products more aggressively, more effectively. All right, HA has a Ka of this. HB has a Ka of this. Could HB actually be more acidic, like have a lower pH, more acidic pH? And the answer is yes. But we'd have to do what? Ramp up the concentration. And that will allow us to push farther. Alright? And again, this is just explaining that. Alright. We have a sample of 0.1 molar HX has a pH of 4.1. Determine the percent ionization. What is the Ka? Alright, so let's walk through this calculation here. We have HX plus H2O yields H3O plus X negative. These are just ice table calculations. Much like we had in the last chapter, 0.1 is my starting concentration. Water is not playing a role. This would be a Ka equals concentration of H3O plus, concentration of X negative, and concentration of HX. Keep in mind, if I want to know Ka, I need to fill out this table so I can get everything filled out. So, minus X, 0.1 minus X, plus X, plus X, X, and X. And there was none to begin with. And it says here that the pH is 4.1. That is the level of H plus ions at equilibrium. So 10 to the negative 4.1. Alright, second log, negative 4.1 equals 7.9 e to the negative fifth. 7.9 e to the negative fifth. That's going to get plugged into here. And it's also going to get plugged into here. So it's 7.9 e to the negative fifth squared over the original. I'm going to use my, you could plug it if you want, but that's basically going to be 0.1. That's our shortcut rule in action, and there we go for our Ka value. It's starting to get on, a bit off of what we normally would calculate, but Let's calculate it out. Square that top number and divide it by 0.1 equals 6.3 e to the negative 8. If I didn't make a mistake. 6.3 e to the negative 8 is my Ka value. Alright, and then what is this guy here? What's the percent ionization? Well, it starts at 0.1. And how much flipped over? Not a lot. Okay, that's this guy right here. So it's going to be percent is the amount that changed divided by original. Alright, so percent changed. Alright, so it's going to be 7.9 e to the negative 5th divided by 0.1. So not a lot of it times 100. Very low percent ionization here. I got 7.9 e to the negative 5th divided by 0.1 times 100, and I'm still only getting about 0.079%. Right, so a couple examples of just different types of problems here. Okay. All right, so take a minute, pause. This is a little more of a baseline problem. All right, pause it out and try it. Alright, hopefully you have a chance to try this out a little bit. First of all, I'm going to run through the answers here. Take time to pause yourself out and see if you get caught or not. First one, HI. You say, okay, well, how do I get the pH of HI? Well, this is a strong acid, so it's just going to be straight up negative log of 0.20 equals 0.698. 0.698. And this guy here is going to be, all right, weak acid, and there's the Ka value for this guy. Okay, so in this case, and these are probably examples that you're going to see on a test. This would be a good example. It was just kind of what we do. We did a few other examples, but these are the main ones that come down the pipe. So this is the ones you want to, make sure you understand or can do. So in this case, I want to find my pH. So I'm going to go HF plus H2O yields H3O plus F negative. Initial split ratio n, this is 0.2, not playing a role, 0, 0, minus x plus x plus x, 0.2 minus x, x, and x. So it's going to be 6.6 e to the negative 4 equals x squared over, I'm going to just use my shortcut rule right away, 0.2. Small k value says I can use my shortcut rule. I want to solve for x to get my pH, so multiply times 2 and square root. So 6.6 e to the negative 4th times 0.2 square root the previous answer equals x equals 0.0114. Now that's the concentration of your H plus ions. In that case, you should, to get pH, negative log this thing, and negative log your previous answer, and you're going to get 1.93. 1.93 is your pH. Alright, now you notice that this guy has the same concentration, but it has a much smaller Ka value. So same starting material, but you're not able to push as far towards products as you would think. Let's see how that affected our pH. This guy is quite acidic, by the way. So it's going to be very similar. Only thing different in this calculation is I'm going to swap out a different Ka value. So I'm just going to do that. 6.2 e to the negative 10th equals x squared over 0.2. Now this is where I mentioned earlier, these calculations really are all identical. They look very similar. Multiply 2 times 2 square root. 6.2 e to the negative 10th equals times 0.2 square root. And I get x equaling 1.1 e to the negative 5th. And we're going to negative log this thing in order to get this your H plus concentration. Negative log that, and we get negative log previous answer, and I get 4.5. 4.95. Alright, so you'll see here that we have a significantly larger, of course you might say, oh, it's not that much bigger, but remember, this is an exponential scale, okay? So it's like tens of thousands times more. It's essentially each one of these numbers here is a 0 spot. So almost 5 zeros over. So almost 10,000 more. All right. All right. One more here coming down almost to the end here. All right. pH of this guy. Pause and try. All right. So here they're giving you this guy here. So a little bit tougher here. Ka times Kb equals Kw. If that's the case, now pause it and try it if you're stuck there. So it's going to be 1.0 e to the negative 14th divided by 1.8 e to the negative 5th. And I would like to just do that math here. 1.0 e to the negative 14th divided by 1.8 e to the negative 5th. And I'm getting a Ka value of 5.5 e to the negative 10th. And then let's just run this thing through. Now, what part makes this a little tougher is that this chlorine cannot, it's just, when it dissolves, it floats off by itself. And I got this guy is the one that really makes it acidic. So, there we go. Plus H2O yields H3O plus NH3. Alright, initial stoichiometric ratio N, 1.5, pretty concentrated. 0 and 0, minus X plus X plus X, 1.5 minus X, X, and X. Alright, I'm just going to plug in these values here into my expression. Ka equals the concentration of H plus ions, concentration of NH3, over the concentration of NH4 plus. I want this guy right here. Okay. Gives me my H plus ions, I can get the pH. So the Ka value is 5.5 e to the negative 10th equals X and X and 1.5. I'm going to use my shortcut rule right now. There we go. Math a lot easier. Multiply over, square root, okay, times 1.5, and then square root that particular value. And I get 2.8 X equals 2.8 e to the negative 5th. Now, finally, down the end, let's log this thing to get our pH. Negative log, previous answer, and I get about 4.5. There we go. That is it. What have we learned here in this thing? Emphasized. Okay, basically we have a couple different types of things we want to do. We have theory, and we have actual calculations. The main calculations you want to be able to do. Like, I wouldn't worry about anything else unless you can do these two, which is the pH of a strong. Okay, just negative log an actual value. That's going to show up. And the pH of a weak. Again, that's something where I just give you a Ka, I give you a concentration, and you determine the pH. These are two calculations that are first in line. Theory, remember we have Kas, Kbs, we have concentrations of each, and can you just, without any math, look at and see how something is likely to be acidic or likely to be basic based on this idea. And we'll stop there. Thank you very much.